So in this talk, I would like to present some of the applications in which we use 3D vision to give a cutting-edge advantage to our systems that we believe may change the way pilots fly aircraft and analyze scenes in real operations. I will also go into some details regarding problems we encountered on the way and how we went about solving them in order to fit this academic conference. Okay, so the first application I would like to talk about is for the rotary wing aircraft family. And it's called the Degraded Vision Environment Mitigation, or DVE mitigation in short. So what is considered DVE is shown on this slide. So we have aircraft-independent degraded visual environments such as smoke and clouds and dust. And we have aircraft-induced degraded visual environments such as whiteout and brownout. Brownout is when an aircraft approaches the ground for landing and the rotary wing swirls around all the dust and sand from the ground, and it kind of creates a brown cloud that the pilot can't see through, so he can't really see where he's trying to land, as can be seen on these images. So what we're aiming at is actually turning this model upside down. So instead of being making it very difficult to perform operations under these conditions and trying to deal with very deadly and situations, we want to give the pilots the ability to see under these conditions and fly deliberately under these conditions with confidence and safety. And we do this by allowing them to see. So in our system, we have mounted on the aircraft several sensors, active and passive sensors, which have a good vision under these conditions. And then we have a processing unit on the aircraft that collects all the data together and meshes it up to create a 3D model with texture applied onto it. Then we render this model from the line of sight of the pilot and project it onto his head-up display, his or hers head-up display. So when the pilot looks outside the window, they actually see our synthetic vision overlaying the real scene, which they can't really see. So our flow, this is our algorithmic flow for creating all these, creating the 3D model. And of course, it's wrapped up with databases and sensors. So we first render, okay, so we render images from our navigation system, IGI, embedded GPS inertial navigation system, and we have our radar and LiDAR measurements, and we first sync them all in time and position. We process each one separately for outlier filtering, and then we do our measurements go on spatial registration using detailed digital terrain from our database. And then after this step, all the measurements are in the same coordinate systems, in the same location, so we just have to fuse the different point clouds. And here we fuse the measurements from the current point clouds with previously recorded point clouds. And of course, the fusion is processed according to the figure of merit of every single measurement and its credibility. So after this step, we have probably still a noisy point cloud, and we want to improve it and segment it for morphology detection. So in the next step, we can create our mesh, our surface from these point clouds. We do additional fairing, and then we apply texture onto it from our database of satellite images and from currently rendered images in different bands, the visible band and IR band, which are separately fused together and then applied onto the texture. So then after all these steps, we have in our database our 3D model, which we can render onto the, from the pilot's line of sight and project it onto its display. So the second application I would like to discuss is sky, or sky eye, as we call it. And this is a wide area, high resolution, airborne persistence video surveillance system. And this is a very long sentence. And in shorter sentences, what it describes is as follows. We have an aircraft, usually a UAV, circling a large area at the height of a few kilometers. And on this UAV, we have a high-resolution camera, which constantly records videos of the whole area. So this is a lot of data to process, and we usually want to process it in real time. So here we use 3D vision to automate some of the processing we do on this database, such as detecting infrastructure changes and understanding the scene to plan routes of motion. So this is very useful in case of battle zones or disaster-stricken areas. And our pipeline for creating this is as follows. We have the first step where we take this very wide area and split it into smaller zones so we can process them all in parallel. And then we create our point cloud using the images collected for each zone. Then we go on to mesh creation, and finally we merge and applying texture onto it, and finally we merge all these zones together to create the whole area. So if we dive into the point cloud creation, we have two major steps here. The first step is creating a sparse point cloud, which is aimed at improving our measurements of the position and orientation of the camera, taking at each time of the camera for each image used. And the second step is creating a dense point cloud from the images and the measurements of the location and orientation. So our first steps are pretty common. We have point matching, which we use optical flow because we actually have a good initial guess about our position and location in the images. And then we do some triangulation to create our point cloud, and then we use bundle adjustment to find our corrected locations and orientation. Then we really want to go on to the next step of creating the dense points cloud, but here we encounter the problem because the images weren't very good. Weren't very good to start with because we have our rolling shutter effect. So this is an image I really wanted to work, but we couldn't manage to make it work. But what we should be seeing here is a wobbly effect of the images because our images are our camera is a rolling shutter camera, which means we have an array of sensors which are exposed consecutively. And we have those in our mobile phones, but in our case, the camera is mounted on an aircraft which has very high frequency vibrations, and also our rolling shutter is pretty long. So we have this effect, and it's really, it's not really a good idea to create a mesh with these images as is because they create very noisy point clouds, and we also may have, oh no, and we also may have waves in our point cloud. So what we do to solve this problem is as follows. We follow the first steps of tracking points and then creating a point cloud by triangulation. And then we project back each point from the point cloud to its original image. And as we can see, they land at a different location from where they originated. And this is because when we do our mesh creation, we use several images, so we do have an effect of canceling out some of the noise, but not quite all of it. So what we do, we take all those back projection errors and map them onto the image according to the location. We can see our wavy effect right here. And this is the effect we want to cancel out. And we can do this if we have a good parametric model. Luckily, I'm skipping a few steps here because the time is running out. Luckily, we do have a good model because we have a good understanding of our platform. And we mapped each cause of noise in those images and a good modeling transform for them. So we have ground height errors, for example, which can be modeled by shift, and we have accelerations and low frequency effects, which can be modeled by polynom. And we have vibrations of the gimbal and high frequencies, which can be approximated by a series of harmonic functions. So here's our model that accounts for all these noise factors. And we can fit the parameters of the model for each image and then correct the images so we are quite ready for our next steps of creating the dense point cloud. So the next step would be plane sweeping, which is also a common technique. We want at this step to create depth maps from a few viewpoints around our circle. So we have from our initial, using our initial point clouds, we have a good guess of the planes in the image. So we start sweeping planes. And every plane is a hypothesis. And according to every plane, we warp images to the reference image, and then we compare the images with normalized correlation, and we get a score value for every pixel in the image. So at every height, we have a score for every pixel, how much this pixel matches this height. And as you can see here, this is our plane sweeping from the highest level to the lowest. And we can see that as the pixel fits that plane, that pixel would turn red in the image. So after that, we use some Markov random field image labeling to add some normalization and choose the height for every, pixel. Okay. So then we create our DSM, and I'll skip this, skip some slides here. We create our DSM by merging the different depth maps together. And then we go on to mesh creation. And here we also have some steps I won't elaborate on, but we create the mesh, and then we simplify the mesh and apply texture onto it and do some texture blending. And if I'll dive into texture mapping, then we have all the images from the circle, from the whole circle, and it would be ideal if we could just map one image onto our mesh. But this is quite impossible because in each image we have some hidden areas. So what we do is we map in our mesh each triangle to the image that sees its best according to its normal. For example, here we have this wall that can be seen best from this image, and this wall can be seen best from this image. So if we map each triangle to the image that sees its best, then we'll probably have a lot of transitions on small objects like cars in this case, and this doesn't really look good. So we translate our mapping problem into a graph labeling problem, so that in our graph each node is a triangle, and the edges between the edges in the graph are edges between triangles, and what we want to minimize is that every triangle, we go to the image that sees best, and we want to minimize the amount of transitions between images. So we want every triangle to go along with its friends or neighbors to the same image. So this would be our image before we use the graph labeling problem, and this is our mesh, and this is after we apply the smoothing with our solution, and this is what our mesh looks like. And this is a view of our okay. This is a view of our model as rendered. And just a short example of the application and why we worked so hard to create this very accurate point cloud and model. Here we can see videos from 2 flights around the same area, different time of the year, different height, different image quality. But what we can see here, I don't know, can anyone tell the differences in infrastructure between those 2 images? Okay, so so this image right here has some staging around it in the second image here. And this is pretty much hard to detect in real time, but when we compare these 2 models in 3D, we can see that this is the difference image, and the staging are marked right here. We also have some differences on trees because of different leafage at different seasons of the year. So I'd like to thank our outstanding team for doing it great work. We have a lot of projects, of course, and not only the ones I presented here. I would especially like to thank Hadas Kogan and Lior Barak for doing most of the work presented on these slides, and we would love you to join us.